Okay, I did record class this morning, Friday morning, but the software crashed after making the recordings and I could not retrieve the files, so this is a recap of class. I'll definitely be able to get through it a lot faster than 50 minutes. The first part of class we talked about sine and cosine functions, so let's just write those down. The rate of change of sine x with respect to x, we worked out graphically that that's cosine x. We saw by looking at what's called local linearity, by zooming in on the curve until it appears straight, we can calculate approximate rates of change. And by doing that in a few different places, we saw the pattern emerging that the rate of change is cosine x. And then I just told you that the rate of change of cosine x with respect to x is negative sine x. You can go through that same, just take the cosine curve and 3 or 4 different places along the way, look at the local linearity and estimate the rate of change and plot those points, and you'll see quickly that the graph that starts to form is minus sine x. Okay, so the bulk of class was about composite functions. So let's review what composite functions are and then how do we calculate their rates of change. So the main example we've seen of composite functions this semester was this r of left of x. Now, we should also mention that we didn't use it a lot, but similarly there's r of right. We can similarly do r of right of x, r of mid of x. And the idea here is a process of going through two functions in succession. That's the idea of a composite function. That we have a first function, in this case it's the left function, in which x is the input. And the output for this particular function is another x value, the x value at the left side of the interval that x was in. So this is the output of the left x function. But in this composite setting, that left x value also becomes then the input into the next function, which is the rate of change function, r. So the output then of that is the rate of change at the left end of the interval that contains the original value x. So just a picture of that. We've got intervals like this, delta x intervals, right? So we come along here and we pause x. We say x is right there. So left x, plugging x into left x, outputs this value right here. And then we take that output of left x and we put it into the rate. And so then whatever the rate is, whatever the rate is at that point, is r of left of x. So this y value, we got a rate function here. The y value of the rate function at the left side is r of left of x. So that's just to kind of get us the idea of composite functions. We have seen it before this semester. But in general, composite functions have lots of applications and we see lots of them. So just in a generic sense, we can talk about the composite function g of f of x. So what would that process be like? So you should ask yourself, what's the first function that is in this process of g of f of x? And the first function is, you should be thinking that it's f, and it is. And the input into f is x. And so f spits out some output f of x. But that output then in this composite situation is then the input into g. So f of x is both the output of f and the input of g. So that whatever that value is, goes into g, and out comes this final value, g of f of x, which is the original input x being put through the f function to get its output, then that output put through the g function to get the final value of g of f of x. Okay, so here's some functions that can be seen as g of f of x, and this is important to be able to see them this way when we start to apply finding the closed form rate of change of these composite functions. We have to be able to see them kind of as these two pieces composed together. And let me just mention that another notation for this would be g composed with f of x. So when you see that notation, you just have to remember that the first process that's represented here is the f process. So x goes into f first, and then g. So this kind of shows that a little more explicitly, that x is going to f of x is going to g. So when we use this notation, we just keep the same order, left to right, g, then f, then x. So keep the same order. But just remember that f comes first. Okay, so f is our kind of our interior function, or the first process function, and then g is the outer, or the exterior function. So what output f of x is then the input into something, g, so that we get this result. Well, here we can think of that as the input into square root. So we can think of the f(x), the interior function, as x cubed minus 5. To get h of x, that output of f then becomes the input into square root of x. And we talked about that there's other ways, another way to think of it. But when it comes to finding the rate of change in closed form, this is going to be, if we were to find the rate of change of the closed form of h, this would be the way that we will want to set up f and g. Okay, for p, we got e to the 3x to the 8th. So what is being plugged in to what? Or the output of what function then becomes the input into an exterior function to give us e to the 3x to the 8th. Well, notice that 3x to the 8th is actually being the input into the e exponential function. So 3x to the 8th, if that output of f, 3x to the 8th, becomes the input of e to the x, we get this p function, e to the 3x to the 8th. So that's that one. Okay, this one here, I'll do it up here. Here, natural log is the output of f, and then also the input of g, (1 over x). So if the output of f, ln of x, was the input of g, we would get this function v of x, which would be 1 over ln of x. Okay, we saw in the second class that this one is a little trickier and kind of beyond the level of difficulty that we need right now to get the idea of composite functions. So we'll just skip over that one. Here's another one. So our interior function is 1 over x. It becomes the input into the exterior function, which is sine x. So 1 over x, its output then as the input of g, gives us the function sine of 1 over x. Okay, so that gives us the idea of kind of how these composite functions work. And we'll come back to these examples at the end of the video, I'll come back to these and I'll actually solve all of the rate of change of all of these functions, well, excluding this one. We'll do these four just so we can get some examples of how finding the rate of change of a composite function works. So let's move on. So here is e to the 1 over x. I've set up the open form rate of change function given any function f that I put in here. So if I graph the open form rate of change and I've got h plenty small, we can find out if indeed the rate of change function for e to the 1 over x is the same as e to the 1 over x. And you see it's quite different. Not even close. So this is this idea that we need something different when it comes to having, so that this is a composite function, right? The interior function, 1 over x. The output of 1 over x then is the input into e to the x. So composite function is a different animal than just plain old e to the x. We don't have this this equivalence of the rate of change and the original function. In order to make sense of this, then we need to review the meaning of rate of change. So before we go through this and I talk through this, let's remember our constant rate of change. Constant rate of change, remember that we said, what is a change in our quantity? A change in our y value. Okay? It should come to mind. We've been dealing with this all semester. With constant rate of change, a change in our quantity or a change in our y value is equal to some constant times whatever x changes. So this comes first. The change in x comes first. The change in y then is some constant multiple of that. Remember that constant rate of change meant that changes in x and y are proportional. So now we don't have constant rate of change, but if we take h values small enough, we can get good estimates assuming constant rate of change. Because remember we said with a curve, if you zoom in close enough, it appears to be straight. So that's the idea of if delta x is small enough, we can get very good estimates because of local linearity using constant rate of change. So here's a situation. We've got this function f and its rate of change function. At 6.1, the rate of change is 3.8. The question is, what does that number mean? And it's a question everyone should be able to answer. Okay? Yes, it is the rate of change of the function f when x is 6.1. But what is that? What is the meaning of that value? So again, it goes back to all our foundational idea of constant rate of change and what this value of k means. Okay, it's a relative size. 3.8 is the size of the change in y relative to a change in x. So changes in y are always 3.8 times changes in x. I really shouldn't say always, because that would be constant rate of change. What I should say is, in the vicinity, in the very near close vicinity of 6.1, we could estimate changes in y as being 3.8 times changes in x. Okay, if we truly had constant rate of change, yes, changes in y always would be 3.8 times changes in x. But for our purposes here, we can just say close to 6.1. We can estimate that any change in y would be 3.8 times the change in x. Or in other words, y is changing 3.8 times as fast as x in the vicinity of 6.1. Really crucial, important concept here. Gotta keep practicing that. And so hopefully by now for a lot of you, this is just, it's not taking long for you to come up with this because we've seen it so many times. But if the questions I'm asking, you're still saying, I just don't know, then it's at some point this idea has to stick. Okay. So here's a summary. This means that if x moves a tiny bit from 6.1, the value of f will change approximately 3.8 times as much. In other words, the change in f is about 3.8 times the change in x. That's what we just kind of spelled out a moment ago. So this idea is going to be really important to grasp what's happening in the two-step process of a composite function. Okay, so let's skip on to that next slide. Okay. So now there's two functions, and we're talking about g of f of x. So what comes first? We know that x goes into f. So we're going to start with a change of x. So if we have a little tiny change in x, the question is, for that change in x, close to x equals 6, what will the corresponding change in f be? Okay, so for a little change in x, in the vicinity of 6, x equals 6, what will the corresponding change of f be? Okay, again, rate of change in y approximately equal to k delta x. Or in this case, the change in f approximately equal to the rate 5 times delta x. This says that the function f is changing 5 times as fast as x. Or for any change in x, the change in f will be 5 times that change in x. So we can illustrate it this way. Here's the corresponding change in f for some little change in x in the vicinity of x equals 6. Okay? So now we're going to look at the exterior function g. So here, from here to here, is our change in f. And f is the input into g. So what will the corresponding change in g be for a little change in f? Here I'm showing from the blue to the blue. There's a little change in f. What will the corresponding change in g be? Take a minute to think about it. Okay, by the same principle, the change in g will be, because of this rate of change, the change in g will be 3 times the change in f. So the change in g will be 3 times this quantity shown here from blue to blue. So this says that output f changed by a little bit, again, delta f. So how much did so that's the same change to the input of g, and the output of g is always 3 times a change to the input. So now we got 3 of those. So 1 delta f, 2 delta f, 3 delta f. So now we want to kind of just make it, if we're thinking about this as one function, for a small change in x, how much will the function g of f of x change for a small change in x? We can see it through the illustration. here's one small change in x. As we go through the process of f and g, results in what multiple of that change in x? Well, there's 15, and that comes from that delta f was 5 delta x, and delta g was 3 delta f. So therefore, the overall change of the whole function will be 15, or 5 times 3 of delta x. So first, the 5, what was the 5? The 5 was the rate of change of f with respect to x. And the 3 was the rate of change of g with respect to f. So that product, 5 times 3, is the rate of change of the whole function. Okay, so given a little change in x, that whole function g of f of x will change 15 times as much as our little change in x. So this is basically the foundation of the chain rule. So we're chaining these changes together. And so normally we write it though with this. We normally will work on this part first. So we'll have a different order. We'll have r of g of f of x. We'll do that first, and then times r of f of x. So this is what we call the chain rule. It's the rule that allows us to find closed form rate of change functions from a composite function. This is summarized on the next slide here. So if f and g are functions having rate of change functions r, f, and rg, then the rate of change function for the composition, this is what we said. And we did this first. We said that changes in f are, we said 5 times changes in x. That was the rate of change of f. And then the rate of change of g is 3 times whatever change in input that we have. So we had a change of this gave us some change of the output of f becomes the input of g, and the rate says that the output of g will be 3 times whatever the change of the input is. So that's where we got the 15 as the rate of change of g composed with f. So the rate of change of g composed with f with respect to x is the rate of change of g with respect to f times the rate of change of f with respect to x. And similarly, we can have the prime form, which is read no differently. We read this exactly the same way using rate of change terminology. Okay, so the key is that we leave when we evaluate that rate of change of the exterior function. We don't do anything except leave. This is the correct way. Leave that interior function as it is when we evaluate that exterior rate of change, and then we come along again here. We leave that interior function just as it is. And then we come along and multiply by the rate of change function of the interior function. So let's take a look now and go ahead and find the actual rate of change of this function. So e to the 1 over x. we showed before. So what is the interior function f? The interior function f is 1 over x. Its output then is the input into the exterior function, e to the x. So when we do the rate of change of this composite function, what's it going to be? It's going to be the rate of change of the exterior function leaving the interior function plugged in. So we look at the structure of this. The big picture of this is the g function. And we're going to evaluate its rate of change leaving the interior function as it is. And so the rate of change of e to the something is e to the something. But then by the chain rule, we multiply by the rate of change of the interior function. So 1 over x we can rewrite as x to the minus 1, and we can use the power rule, which is negative 1 times x to the negative 2, which is simplified as e to the 1 over x times negative 1 over x squared. So before we tried e to the 1 over x to see if maybe that was the rate of change of e to the 1 over x. It's not, but it's part of it. We also need to multiply by the chain rule. We need to multiply by the rate of change of this interior function, which is negative 1 over x squared. So that's our rate of change for e to the 1 over x. Okay, so let's try this one. So you might pause the video here and see if you can evaluate this one on your own. Okay, first we'll look at, again, we want to look at the overall structure of this, or the big picture. The big picture of this, or the g function, is something to the fourth. So that's where we'll start. We'll evaluate, when we evaluate the rate of change of h with respect to x, we'll start with evaluating the rate of change of this g function, but remember, leaving f, the interior function, as it is. So 4 x squared plus e to the x cubed. Now times, and by the chain rule, we remember that we need the rate of change of the interior function. Rate of change of x squared is 2x. Rate of change of e to the x is e to the x. So earlier we had tried this function as the rate of change to this one. Saw that it was incorrect. Why is it incorrect? Because we need to chain on the rate of change of the interior part. Let's go back to that previous slide that has some more examples, and we'll finish up with those. Okay, so these are all good practice except this one at this time. This isn't a good one, a little too complicated for us at the moment. Okay, so these are all good practice. You might pause the video and try them yourself before I go ahead and do these. So I'll write it this way. So the rate of change of h of x with respect to x. Again, the overall structure is radical something. Radical something. That's like our g function. So we're going to start with the rate of change, Remember we said that rate of change of a radical function is 1 over 2. Remember we leave the interior function as it is. So we evaluate the rate of change of the exterior function, leaving the interior function as it is. Then we multiply by the rate of change of the interior function, which is just 3x squared. We can simplify that final product, 3x squared over 2x cubed minus 5. Okay, this is the rate of change function for this function h. Okay, p to the x. So the rate of change function for p to the x equals, so you ask yourself, what is the big picture of this, or what's the exterior function, or what's the overall structure? Well, the overall structure is e to the something. The rate of change of e to the something is e to the something. And remember, we leave the interior as it is. Then, by the chain rule, we need the rate of change of the interior function, which will be 24 x to the 7th. This is the rate of change of e to the 3x to the 8th. It's e to the 3x to the 8th times 24 x to the 7th. Okay, we're not quite ready for this one yet, but I guess we're not going to prove it, but the natural log, the rate of change of natural log is 1 over x. That's a rule that we hadn't seen yet, a rule for finding a closed form. So the closed form derivative or rate of change of natural log of x with respect to x is 1 over x. So now we can use that fact to solve this one. So v, what's the big picture? What's the structure of v? Well, it's 1 over something. Okay, so 1 over something is like x to the minus 1. So it's like we have, so v is like natural x to the negative 1. We can apply the power rule first, which says exponent out in front, reduce the exponent by 1, leaving the interior function as it is. Then by the chain rule, multiply by the rate of change function of the interior. And I just showed you that the rate of change of natural log of x is 1 over x. So making this look a little prettier here, we got a negative, and we have in the denominator we have ln of x squared, and then we have an x. Oh, sorry, this is not right. That just should be, that should just be prime, signifying rate of change function. So this is the rate of change function of v. Okay, one more is q. Again, we look at the overall structure, which is sine. Sine function is the overall structure of that. So we're going to start with taking the rate of change function of sine, leaving the interior function as it is. So the rate of change of sine is cosine. And we leave the interior function as it is. Then, by the chain rule, we need the rate of change of the interior function, which is negative 1 over x squared. Again, this is x to the minus 1. Rate of change, negative x to the minus 2, which is that right there. So I can simplify this as cosine of 1 over x over, so the opposite, actually, just pull the negative out here, negative cosine 1 over x all over x squared. So one more time. The rate of change of a composite function is the rate of change of the exterior function times, with the interior function left as it is, and then by the chain rule, times the rate of change of the interior function. Okay. Good luck. See you on Monday.